All right, so for number 11, it says the nursery owner claims that a recent drought stunted the growth of 22% of all her evergreens. The botanist tests this claim by examining a simple random sample of 1,100 evergreens, all right, and finds that 268 trees in the sample show signs of stunted growth, with the null hypothesis P of 0.22, alternate P not equal. What's the value of the test statistic? All right, so for this, we go to our handy dandy. Let me just pull it up over here. I forget where I put it. Formula sheet. All right, we're talking about a population proportion. Oh, lordy. All right, so it's population proportion. So from our available formulas, it's a single population. So, well, all the choices kind of lend themselves to that anyway. All right, so the formula that we want is going to be P hat minus P over the square root of PQ over N. P times 1 minus P, I should say. All right. So one population proportion, or P hat, X over N, which is going to be 268 over 1,100. All right. So 268 divided by 1,100, that's about 0.244. And you can see that that is pretty much everywhere. So no help there. The P, the assumed P, is the 0.22. That's coming from the null hypothesis. So also no help there. We can start crunching the numbers. The other approach that I kind of hesitate to recommend here is to put the information in your calculator and check it against all of your possible choices. That's a in case of emergency break open glass kind of situation. Right? So it's definitely more of a brute force approach. In this case, I would just say, or Z, and it's important to remember that when you're talking about, it didn't come up in this problem, but when you're talking about a test statistic, it's Z, T, or chi-square, right? The chi-square cases are usually a little bit more obvious, but in the case of a population proportion hypothesis test or confidence interval, it's a Z distribution because it follows binomial rules, and binomial is a special case of a normal distribution, right? So 0.244 minus 0.22 all over the 0.22 times 1 minus 0.22 over my sample size, which is 1,100. All right. So, and again, that comes right from the formula sheet. It's on the back of the first page, and it's one of the first options there. There is an instance where you could use the P hat in your standard error. So these values here, instead of using P, it could have been P hat. I kind of dismissed that as a possibility because the only relevant formula was this one, and pretty much all of them were populated with the 0.22 instead of the 0.244. Right? But there is a world where that would be the case, and that's usually when you don't have a reasonable assumption that the P is actually, whatever it is in this case, the claim of 0.22 is actually correct. All right, if we think that it's more leaning towards the alternative hypothesis, something other than 0.22, I would use a 0.244 in here, but that's not the case here. So D it is. I look at it, there's definitely some typos in here. I'm not really sure where these twos came from, but they really shouldn't be there. I think that's just no way else to say it, typo, because this would be the correct formula. And actually, you know, while we're here, we can verify it. And I'll show you. If you go to inference, tests, one proportion, put in the null of 0.22. Alternative, they had it as a not equal. Go to next. Put in your important information. The 268, the 500 becomes an 1100. Significance level, well, it really doesn't matter. I'll leave it at 0.05 because we're just looking for a test statistic anyway. So we'll do that. So this should be about, so I'm kind of using the technique I said earlier not to use, but in the case of a typo in a practice problem set, you've got to figure it out somehow, right? So that would be 1.892. And then when I go into my calculation app and type this in, 0.244 minus 0.22 divided by the square root of, and there's also a quirk with this technique also. I'll explain that in a minute. But it should get us close enough to this value that we can feel some sort of level of confidence. Pun intended, maybe. We'll see. 1.922. That's very close, right? So it's right in the neighborhood. Again, the drawback on this is that the calculator actually uses the variation of this formula, where instead of it being p hat minus p, that all stays the same. But if you're not convinced that the null hypothesis is true, then you go with the p hat version of this, which would be this formula. All right, so there's all kinds of things wrong with this problem. They didn't give you enough information in order for you to determine that it should be this formula as opposed to that one. And then in their choices, they really kind of like, I don't know, they messed it up royally. So the closest one I have is this one. When I wipe out the extra 2 that was there for no good reason. If it was asking for a p-value, it'd be a different story, but that's not what they're asking for. So gotta love it. All right, so number 12, medical research team tests for tumor reduction in a sample of patients using 3 different dosages of an experimental cancer drug. Which of the following is going to be true? 3 explanatory variables, 1 response. 1 explanatory with 3 levels of response. 3 different dosages. That's a single drug, right? So this is my explanatory variable. Or really, it's the treatment. But we want to know if this treatment is going to cause some sort of change. So we'll treat that as the explanatory variable. All right. So in this case, it's not always true, but in this case, the treatment is an actual treatment, in theory. The dosages would be the different levels. Right? So we would be looking at 3 levels of a single explanatory variable. So choice D. Right, that's really what's going on there. Graph below shows a cumulative proportion plotted against age for a population. You want to know what the approximate value would be for the median. Right? So if it's a cumulative proportion, all we're really looking to do here, get a little dotted line action going on here, estimate where 0.5 is and see what that corresponds to in terms of an age, because the median is the 50th percentile, and there's nothing close to A, so we would select that. A cumulative proportion is, in many cases, thought of the same way as a percentile rank or percentile value. So you can just look for that 0.5 and be done with it. All right, so that's kind of a not too bad one. Number 14, Mr. B's stat class had a standard deviation of 11.2 on the standardized test, while Mr. M's had a standard deviation of 5.6 on the same test. Which of the following is the most reasonable conclusion concerning the two classes' performance on the test? So we're talking about when they're only giving us standard deviation here, so we don't know anything else. We're looking at variation, right? So it's some sort of measure of variability, right? So how spread out the data would be. So we can't really say anything in terms of like B, sorry, not B, C twice as well. I don't know how we would be able to determine that, because it's possible. I'll just give you a quick example. If you have some sort of distribution, I'll draw it like a normal, but it really doesn't necessarily have to be, with some average in the middle. So we'll call that X bar, and we'll say that this is for Mr. B. And that X bar, yeah, it could be whatever. Let's say it's a 90. The standard deviation is a measure of spread. So we're saying we would go out one standard deviation, about 11 and change. All right, that'll get us over here. Then two standard deviations, and three standard deviations. So it'd be like 101, 112-ish. I think it was 11, right? 11.2, I'm just leaving off the decimals. So 123, like 79, 68, 57. So that's where you're living, all right, in that neighborhood. Now, another example could be that in this case, Mr. M could be centered around the same 90, but now going out in 5-unit increments-ish. So 95, 100, 105, 85, 80-ish, 75. Now, I'm not doing this so that you can say, okay, well, I guess I got to do this on the exam. I'm doing this because I want you to kind of understand the idea is that I just made up that 90. This is just telling me how spread out the data would be. Within 3 standard deviations is considered not to be in the outlier territory. Anything outside of 2 standard deviations is considered unusual. All right, so in the case of Mr. B, anything outside the interval of 68 to 112 would be considered unusual. In the case of Mr. M, everything outside the interval of 80 to 100 would be considered unusual. But we can't really make a determination like of size. Right? I could have done the exact same thing, but just put this center value at 70, and I would still have the same shape of the distribution. All right, so we can't make a determination on that. We certainly can't determine that, right? Because this data set says just as well, maybe even better. Mr. B's class has a higher mean, but it might not be statistically significant. Sometimes they'll throw in a choice that will kind of, in the wordiness of it, make you think, well, that sounds statistically significant. That sounds like a very intelligent answer. That must be the right one. It's not often the right one. So in this case, we still, no matter what terms they use in it, we can't make a determination based on the information that was given whether one set has a higher mean than the other. All right. Heterogeneous versus homogeneous. More spread out would be heterogeneous. All right. More tightly grouped would be the homogeneous, right? So they're going back and forth on that. And again, it's the wordiness of the problem that's kind of designed to confuse you. The Mr. M's group is more tightly grouped than Mr. B's. So that's going to be the more homogeneous set. Mr. B's class is less tightly grouped or less loosely grouped because heterogeneous is going to be considered the opposite. So that's really contradictory. So that wouldn't be the correct one. So it would be B. All right. So they try to get you with the wordiness of it, but it's really It's really all about the variability. 15 college admissions officers interested in comparing the SAT math scores of high school applicants who have and have not taken AP Stat. She randomly pulls the files of 5 applicants who took the AP Stat and 5 applicants who did not, and proceeds to run a t-test to compare the mean SAT scores of the two groups. Which of the following is a necessary assumption? All right. So we have population variances are known. Well, not if it's a t-distribution. All right. If the population variance goes hand in hand with population standard deviation, right? So if I know the population variance, I'm most likely going with a z distribution rather than a t distribution, right? The population variances from each group are unknown. It's a small sample. I'm still thinking it's a t distribution, so that's a possibility. Right. So move on. C, population variances from the two groups are equal. Again, another possibility. The population of SAT scores from each group is normally distributed. That's actually one of the conditions of using a t-test, is if you have a small sample that you know it comes from a population that is normally distributed. So that, out of all the ones that could make sense, this is the one that would actually have to be true in order for you to use a t-test, right? If the sample size was large enough, then it might not even be using a t-test. And I also go back and look at the metrics here. We're investigating. She randomly pulls the files of 5 applicants and proceeds to run a t-test, right? So the things like n times p and n times 1 minus p, that's for a population proportion, right? Right, that's the rule of sample proportions. That doesn't apply in a t-test. So it's a good piece of information, and if you're dealing with a population proportion question, then sure, that would be an excellent choice. But in this case, because of the t-test, it doesn't make sense, so we just go with D. And again, whether or not we know the population variances, whether it's known, unknown, whether it's equal between the groups, that's not necessary assumptions. There has to be an assumption of normality involved in order for really most of these things to work. Right. 16, the appraisal or appraised values of houses in the city have a mean of 125,000 with standard deviation of 23,000. Because of a new teacher's contract, school district needs an extra 10% in funds compared to the previous year. It's kind of a dated problem, I think. Where am I? To raise this additional money, the city instructs the assessment office to raise all appraised house values by 5,000. What would be the new standard deviation of the appraised values in the city? Right? It's not going to change anything, right? Because they're asking about the standard deviation. If you increase every value by the same number, like regardless of all this extra information they gave, it's not going to change your standard deviation. It doesn't change the relative positioning between points, right? So again, a standard, if it goes back to this one, the standard deviation is your relative position around the mean, right? So if I took Mr. M, same distribution, and made my mean 80, I'll do that in red actually, then this would be 75, this would be 70, this would be 65, 85, 90, and 95. But the spacing between parts of the graph would not change. That's the variance, or the impact of variance, right? So we would not have any change in the standard deviation just by adding or subtracting values from the set. Now you get into multiplication, it's kind of like a stretch and skew from Algebra 1. if you have, these are really just translations. So we're doing a vertical translation, for example, or a horizontal translation. It doesn't change the proportional relationship within the figure. All right, and then in this case, the figure we think of as the distribution of data. All right, number 17. A psychologist hypothesizes that scores on an aptitude test are normally distributed with a mean of 70 and standard deviation of 10. Random sample of size 100. Scores are distributed in the table below. The chi-square goodness of fit test. So again, you can do it in the calculator and then check each one of the choices. And, you know, maybe based off of that problem that we did before, we might run into that situation if there's like a typo here or something. But the general rule is that your chi-square test statistic is going to be the sum of the observed minus the expected values squared. And this is all in your formula sheet. I'm just double checking that I'm not lying on that. Where are you, chi-square? Yeah, it's at the bottom of the first page. All right, so it's the observed minus the expected squared. I write it a little bit differently, divided by the expected. All right, so the sum part of it is accounted for, well, this is going to sound foolish, but by the fact that they're all added together. All right, so every one of them has a sum, so no help there. What we do is we find the expected value. If it's a goodness of fit, there's a couple of ways it can boil down. One, we could assume it's an evenly distributed set, right? The other possibility is maybe there's some sort of scheme behind how it is distributed, all right? So, but you'll see in our choices in every case, we have, well, maybe not every case, but you see the 10, 40, 35, and 15. These are the actual values. These are the observed values. This is what happened, right? That's how it just kind of played out. Again, a psychologist hypothesizes the score on the aptitude test are normally distributed with a mean of 70 and a standard deviation of 10. We'll get to that in a minute. This is the distribution of, so the psychologist graded a bunch of papers. I'm assuming that there's some sort of IQ test or whatever. They say aptitude test, not sure what that means. But 10 individuals out of the 100 got a value less than 60. 40 got somewhere between 60 and 70, 35, 70 to 80, and the remaining 15 got above an 80. All right, the first thing I'm going to do is check to make sure that these numbers do add up to 100, right? Because it should account for that sample size, right? Because every now and then they'll hide a category. You know, I feel like they've covered the entire domain here, but you could have like a fifth hidden category, which would be all the leftovers. Now, if it's a normal distribution, we can assume a few things, but using our knowledge of normal distributions, we can come up with the expected values. So these are my observed. Now I need my expected values. But first things first, I can start eliminating possibilities because on the bottom, it should be the expected values. So these two numbers need to match up. So any choice where that doesn't happen, wipe it out. It happens here. With also the caveat that your observed value has to be the initial quantity, right? Because when you raise something to a power of 2, sometimes it does, it generally doesn't matter what order these numbers are in. It would still amount to the same thing when you square it. But our observed value should come first, and that seems to be the case here, 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 and here. The problem is these need to be the expected values, and that's not necessarily the case. And again, we gotta watch out for it being a trick question. So we'll keep an eye on this, but we're just gonna eliminate A for now. B, let's see, 10 minus 16 over 16, 40 minus 34 over 34, and so on. It's in the right format, so we're good there. Unfortunately, it looks like C is in the right format. D's in the wrong format. And E is also in the wrong format. Now, in terms of the expected values, so I mentioned this before, you have their mean of 70. So your X bar is in the middle here. It's said normally distributed. All right, the empirical rule tells us that about 68% of the information should lie within one standard deviation of the mean. So if my X bar is equal to 70, this location here would be one standard deviation below the mean. And this location here would be one standard deviation above the mean. All right, that gets us, 60 to 80. And that should amount to 68% of the information. All right, and if it's normal, it's going to be symmetric, so I'm going to get 34% in this interval, 34% in that interval. All right, it only happens to be 34% converted to just a 34 because there's 100 values in the set. All right, so my middle two values should have an expected value of 34. That seems to happen here and here, but we can but investigate further and make sure, because 95% of the data should be within two standard deviations of the mean. So about 68%, that's not an 8, within X bar plus or minus 1s, about 95% within two standard deviations. All right, so if I take my 95 and subtract from it the 68, because I already accounted for 68%, we're looking at about, 13 and a half, so 14%. Although it does say below, right? So actually it would not necessarily be, so that's my bad. It would not necessarily be a second standard deviation, but we do know that everything else is accounted for in these two categories, this one and this one. So if I take 100 and subtract from it the 68, I know that gives me 32 left over, so each of these should be 16. All right, but while I'm here, about 99.7% within three standard deviations, X bar plus or minus 3s. All right, so these values, these expected values match up, so the answer is B. But you got to be careful. I mean, I made the mistake here. I saw below 60, but in my mind I was interpreting it as 50 to 60, and then 80 to 90 over here. So just be careful with things like that. So 18. A talk show host recently reported that in response to his on-air question, 82% of the more than 2,500 email messages received through his publicized address supported the death penalty for anyone convicted of selling drugs to children. What does this show? Right, so, let's look at the choices. Voluntary response, something more about the characteristics of his listeners. I don't think we care about that. The survey would have been more meaningful if he had picked a random sample of the 2,500 listeners who responded. Well, the fact that they chose themselves to respond would be the issue. And it doesn't look like they weren't polled in a more direct way. It wasn't like they were this looks like self-selection. Right? Recently reported in response to an on-air question, 82% of the more than 2,500 email messages received. It doesn't even seem to be a poll. This could conceivably be him just posing a question and then people searching up his email and sending their response. But anyway, control group. No, it's not an experiment, so let's get rid of that. Legitimate sample, randomly drawn from his listeners. And so, no, there's no randomization involved. So I'm looking at A and C. I keep going back to the fact that they're self-selected. And so even if he randomly selected from the 2,500, they still took the initiative to respond to the question in some way. So I would get rid of that and go with A and just say voluntary response sample equals bad. All right. Define a new measurement as the difference between the 60th and 40th percentile scores in a population. This will give us if it's a different, even though it's not a measurement that we use, I just kind of think back to in a box plot. You have the lower quartile, the upper quartile, and the IQR being the difference between the two. Upper quartile minus lower quartile. And we think of that as a measure of variability. It wouldn't give us anything. It's just giving us the relationship or corresponding to spread. It doesn't tell us anything about center. I mean, aside from the fact that you know that the median is going to be in there somewhere between the 40th and 60th. Yeah, so it's in there, but it doesn't really lock down where that center value is. It could be anywhere in that interval, right? And just to refresh your memory, this is lower quartile is 25th percentile, upper quartile is 75th percentile, right? So it's more analogous than actually correct. But we wouldn't be able to tell anything about symmetry, skewness, clustering, not enough information. And again, central tendency like mean or median, we wouldn't be able to determine, so it would be B here. Suppose X and Y are random variables with the expected value, another name for mean, of 37 and the variance of 5. And then for the Y variable, so different variable, E is equal to, or so the expected value is 62, the variance is 12. What's the expected value and variance of the random variable X plus Y? Well, let's see. If you add two means together, the result is the sum of those two means. So I can add these two. That's going to get me a 99. That's there. Okay, so no help there. If the two events are independent of one another, which they don't really say anything about, you can add the variances, in which case you get a 17, but that's only if the events are independent. There is a crazy nasty formula for dependent situations that'll help you make that determination, but it wouldn't give any of these values first and foremost, and also it's not something that they typically ask on the exam, so I would say that this is one of the rare cases where none of the above would be the appropriate response.